All right, class, let's talk about energy. What is energy? Energy is nothing fancy. It's basically ability to do work. Now, we have two types of energy, and you probably know from physics what they are. One of them is kinetic energy, and the other one is potential energy. Now, what is kinetic energy? What is kinetic energy? Kinetic energy is energy of motion. Is energy of motion. So kinetic energy is energy of motion, energy of moving. Anything that is moving, it has a kinetic energy. Potential energy is stored energy. Potential energy is a stored energy. Okay? Now, let's say I have a bar of chocolate. Now, what type of energy does my chocolate bar have? It's potential energy. Now, as soon as I consume that chocolate bar, then it becomes kinetic energy and goes straight to my thighs, right? So food is potential energy. You consume it, then is kinetic energy. Now let's talk about gas. You put gas in your car. When you put gas in your car, gas is potential energy. When you drive your car, then it becomes kinetic energy. Okay, so you know these things. Now, the other thing to think about is heat. One thing I want you to start thinking about is heat. And the reason that I want you to start thinking about heat, because heat is a form of energy. We don't think about it, but heat is a form of energy. It's thermal energy. So it's thermal energy. So heat is a form of energy. When something is hot, that means things are moving. When something is hot, that means things are moving. So think about that. That heat is actually a form of energy. I want you to remember that. All right. Now, let's talk about the units of energy. Okay. Let's talk about units of energy. Now, if I want to talk about the units of energy, and you probably already know some of the units for energy. Okay, so the units of energy, we have the SI unit is joule. Okay, we have joule, and it would be uppercase J. Now, also, but the more common is kilojoule. Kilojoule is going to be more common. And of course, you already know this. How would you go from kilojoules to joule? 1 kilojoule would be 1,000 joules. 1 kilojoule would be 1,000 joules. So that would be the SI. Using joule and kilojoule is more common. But the one unit of energy that we actually used to seeing all the time is not joule in US. What is it? It's calorie. It's calorie. That's the one you're more familiar with. Is calorie. Lowercase cal is the abbreviation. But also kilocalorie. Also kcal. And the abbreviation for kilocalorie, kcal, is uppercase cal. Okay. So calories and kilocalories. So calorie is we see it all the time, and then kilocalorie, kcal, is another one. And calorie, lowercase cal, and then for kilocalorie, uppercase cal. Okay. Now, how would I convert between joule and calorie? What do you think? So there's a conversion between joule and calorie, and that is 1 calorie is 4.184 joules of energy. I want you to remember that. That 1 calorie is 4.184 joules of energy. So far, so good? Okay. Now, before I move on, this is a good time to talk about something fun. Since we do fun fact in class all the time. You probably had Hershey chocolate, right? Let's say I have a bar of Hershey chocolate and I have a bar of chocolate from Europe, Kinder chocolate, any Belgian chocolate. Which one do you think has more calorie? Hershey chocolate, or if I get some European chocolate? Which one has more calorie? I always thought, it's got to be the Hershey chocolate, right? Because we're the one who are unhealthy. Now, if you look at Hershey chocolate and compare it to any chocolates from Europe, if you compare the calorie content, you're going to be so surprised that the chocolates from Europe has so much more calories than the Hershey chocolate in the US. How is that possible? We're the unhealthy one. What's going on here? Here's what's going on here. When they talk about calorie in the US, most of the time they're talking about kcal. They're talking about kilocalories. Because remember, the abbreviation is the same, except kcal is uppercase C. So you're going to pay attention to that. When they put CAL, is it calorie or is it a kilocalorie that they're talking about? So pay attention to that. That's really key. I'm actually kind of okay with that. If they give me the kilocalories and I'm thinking it's calories, because I'm going to think it's lower calorie than what it is. So lie to me. That's actually good. I think I'm gaining less calorie than what it should be. Okay, but think about this. Everything from Europe, they always put calorie, and the US is actually, they usually put kilocalorie on the labels. So I need you to remember this for the exam, that 1 calorie is 4.184 joules. So joules and calorie are 2 units for energy. Joules is SI, and calorie and kilocalorie you're really used to it. Now, the next thing we're going to talk about physical properties. And one of the things that I'm going to talk about within that, we're going to talk about phase change. We're going to talk about phase change. Now, phase change, you know what phase changes are, right? You know what phase changes are. I have solid going to liquid and then going to gas. That's one phase change, right? Now, let's go over this one by one. If I have solid that goes to liquid, what do you call that phase change? You know this from high school, yes. They call it melting. Now, I want to be fancier than just melting, right? I'm a chemist, I want to be fancy. I can also call it fusion. When you go solid to liquid, you can also call it fusion. Now, if you go from liquid to gas, what do you call it? Hopefully you're yelling at me that, oh, duh, that's vaporization. So far, so good. Now, what happens? Can I go from solid to gas? Oh, yeah. You can do a big jump. What do you call that? That's sublimation. You've seen sublimation. Where have you seen it? Dry ice, right? Dry ice, it goes from solid to gas. Sublimation, dry ice is a good example. Now, let's go the other way. If I go liquid to solid, what do you call that? Freezing, right? I mean, some people call it solidification, but I'm just going to call it freezing. Doesn't sound as fancy. How about if gas goes to liquid? What do you call that? Condensation, right? If you have condensation in your car, gas goes to liquid. Can you go from gas to solid? Sure, you can do that. They call it deposition. So, these are my phase changes. You probably know all this, but I just wanted to go over it to make sure that you were pretty good with it. Now, what I want you to do, just how I wrote it, write down solid, liquid, and gas for me. Solid, liquid, and gas. And I need you to remember this, especially when you go to Chem 1B. Solid, liquid, and gas. When you come down, you go solid to liquid and liquid to gas. When you come down, that's an endothermic process. Now, when you go up, that's an exothermic process. Now let's talk about what's endothermic and what's exothermic. Endothermic is the processes that you requires energy. You need energy to make that go, right? Now, if I require energy from a reaction that require energy, if you get the energy, where are you getting the energy from? You're getting the energy from the surrounding, right? You're getting the energy from the surrounding. So if I get my energy from the surrounding, what happens to my surrounding? My surrounding is gonna get cold and I'm gonna get hot because I need energy, I require energy. I'm gonna get it from my surrounding. I get hot, my surrounding gets cold. So if you have an endothermic reaction, which means it requires energy, your beaker will get cold because you're getting the energy from the surrounding. When you have an endothermic reaction that requires energy, the sign for energy is positive. I need you to remember that. Let's talk about exothermic. Exothermic is great. It releases energy. It not only it doesn't require energy, it releases energy to the surrounding. So if I have a reaction in a beaker that is going on, what do you think is going to happen to my beaker? My beaker is going to get hot because exothermic reaction is releasing energy to the surrounding. And the sign would be negative. The sign of the energy would be negative. You follow me so far? So endothermic and exothermic. And think about what gets hot, what happened to the reaction, exothermic, and then my surrounding is going to get hot because I'm releasing the energy. All right. Now, I want you to highlight this and make sure you remember this one. So when you come down, endothermic, go up, exothermic. So positive energy, negative energy. And negative energy just means what? Is exothermic, is releasing energy. Now, we're talking about phase change, right? Solid to liquid to gas. Let's talk about water. And different liquid at different temperature, at a specific temperature, they would do phase changes. So depending on the liquid, at a specific temperature, they would do phase changes. What is that for water? Water would do phase change if I have solid to liquid or liquid to solid. That would happen at 0 degrees Celsius. Or if I go liquid to gas or gas to liquid, it would happen at 100 degrees Celsius. So again, water has at a specific temperature, it will do phase change. 0, it can do a phase change. At 100, it could do a phase change. Different liquid, they're gonna have a different specific temperature that they're gonna do a phase change. But for water, at 0 and at 100, they can do phase change. So what I need you to remember right now, that you have to be at a specific temperature in order to do a phase change. So far, so good? Okay. Now, I'm gonna put up a really big chart on my whiteboard. If you don't have room, definitely go to a new page where you have at least half a page. And I'm going to put a chart up for water, okay? Right here, this is going to be my temperature. I can say in degrees Celsius, why not? And then over here, this is going to be my heat. And remember, heat is a form of energy, okay? And then, all right, let's see. All right, so copy this down. This is 0, this is 100. And let's say this is minus 20. So we're gonna go over this chart, and you're gonna know this chart pretty well. Let's go over this chart together. For water, when I'm right here at minus 20 degrees, what is the phase of my water? I have water solid. Do you agree? I have ice at minus 20. I'm gonna add heat to the system. I'm gonna add heat to my water. You following me? I'm gonna add heat to my water. As I'm adding more heat to my water, the temperature goes from minus 2 to 0. So what's going on here, what I have a temperature change. I'm going to put a T change. Because as I'm adding heat, the temperature is going to increase to 0 degrees. Now, when I'm at 0, what is the phase of my water? Still solid, because all the energy went for temperature change. Once I am at 0 degrees, now if I add more energy to the system, what's going to happen is going to have a phase change. Because you have to be at 0 or 100 degrees for water to do a phase change. So now I'm at 0 degrees, I can do a P change, and this water is going to go liquid. Now I'm going to add more heat to the system. If I add more heat to the system, now what I'm going to do? Now all the energy is going to go to the temperature change. It's going to go to temperature change until I get to 100. I get here, I'm still a liquid because all of my energy went to temperature change to reach 100. Once I reach 100, if I add more energy, then what's going to happen? It's going to be a P change. It's going to be a P change. Okay? So it's going to be water in a gas phase. Now if I keep adding more heat, then it's going to be a temperature change. So, a few things to remember, that as you're adding energy, you're either going to have a T change or a P change. You're going to have a temperature change or a phase change. Temperature change and a phase change cannot happen at the same time. I add energy, T change, and then you can only have phase changes if you are at a specific temperature. For water at 0 or 100 degrees, I can do a phase change. But you have to be at those specific temperature in order to do a phase change. So far, so good? Okay. Now, you've done this many, many times. Have you ever boiled water? You've done it, right? If you haven't, do it after this video. It's kind of cool. So you're going to add water to a kettle and you're going to heat it up, right? And the water, as you heat it up, as you apply heat, the water gets warmer and warmer. Nothing happened. The temperature goes up and up and up. Once it reaches 100, then what's going to happen? Once it reaches 100, then the liquid is going to go to the gas phase. Once it reaches 100, then it's going to go from liquid to gas phase. If I apply more and heat, the temperature of water is not going to get higher than 100. All that energy is just going to go to the gas phase. So you cannot make your water to be higher than 100. Your water liquid is just going to go to the gas phase. So I'm only going to have a temperature or a phase change. They cannot happen at the same time. And for water, you have to be at 0 or 100 in order to do a phase change. Now, the other thing that I want to mention is that as we were doing this, when you come this way on a chart, as you're applying heat, what do you think that is? That is you're adding heat. That's an endothermic process because you are adding heat as we're going up this way. Can we go backward? Sure. You can totally go backward because when you go backward, you're removing heat or you're releasing heat. We talked about it. Endothermic, exothermic. You're releasing heat. So as you go from solid to gas, you're adding heat, endothermic. You go gas to solid because you can also go backward. What are you doing? You're releasing heat. You're removing the heat. So far, so good? Okay. So, temperature change and phase change. Now, here's what you need to remember. What you need to remember is that you need energy. You need energy to do phase change or temperature change. You need energy to do P change or to do T change. So now we are going to go over those equations for energy. Are we good with this? Okay, so this shows temperature change and phase change as we got it. So this is going to be the subject of our video, our lecture today. So now we said to do P change or to do T change, what we need energy. We need apply energy or remove energy to do phase change and temperature change. Now let's go over the equation for those two. All right. So if I need a T change, if I need a temperature change, here's the equation. If I need a temperature change, here's the equation. Equation is going to equal E for energy equal mass, matters how much you have, times specific heat. Specific heat is a constant. You have no idea what that means. We'll talk about it. Times T final minus, yep, that's not final. T final minus T initial. Okay. Now, specific heat is a constant that I will talk about in a second. And the constant will dictate your unit, right? The constant will dictate your unit. Usually, they're in joules over gram degrees Celsius. If that's the case, then the mass has to be in grams, the energy will be in joules, and the temperature will be in degrees Celsius, right? Because in that case, then degrees Celsius can cancel out, this can cancel out, I can end up with joules. Now, sometimes people also write the specific heat as joules over gram Kelvin. If I give you a specific heat, that will be a different number, that this is the unit, then Kelvin and the temperature has to be Kelvin here. So the specific heat unit will dictate your unit for everything. You know that the constant will dictate your unit. And I will go over in a second what specific heat is, but I just wanted to put the equation down. Now, the other thing, so that's the T change equation. The P change equation for phase change is, again, you need energy to do temperature change or phase change. These are hard. Oh my goodness. All right, there we go. So energy is equal, again, mass matters. It doesn't matter, it does matter how much mass you have, times delta H of phase change. And this is also a constant. So this one also, that one was a constant. So this one is also a constant. This one is also a constant. Okay, so these are the two equations for temperature change and for P change. Now, what I'm going to do now, I want to go over the temperature change equation and talk about what is specific heat. Let's talk about what is specific heat. We're going to talk about what is specific heat. What is specific heat? Is a constant. But what does that constant mean? Specific heat is the energy required. Energy required to change the temperature. Energy required to change the temperature of 1 gram of a substance by 1 degrees Celsius. Basically, how much energy you need to change the temperature of a substance. Now, I want to put up a table for you. I want to put up a table, and the table is good. It kind of gives you an idea and put things in perspective. I want to put different elements. I want to put copper, I want to put aluminum, I want to put gold, and I want to put their specific heat in joules gram degrees Celsius. Copper specific heat is 0.385 in joules over gram degrees Celsius. Aluminum is 0.897. Gold is 0.129. Again, they have the same unit. Silver is 0.235. Water, liquid, so water has also specific heat. liquid is 4.184. You've seen that number before, haven't you? Water solid, different phases will have different specific heat, is 2.06. Okay. Water gas, and then the last one is ethanol. Specific heat of water gas is 2.03 and ethanol is 2.46. Alright, so now what does this mean? That means how much energy you need to raise the temperature by 1 degree Celsius, okay? Now, when you look at this, which one has the highest specific heat? Water. Water has a very high specific heat. What does that mean? That means you need a lot of energy in order to raise the temperature of water. And that's good, right? We need a lot of energy if you want to raise the temperature of water, right? That's why, we have ocean, you're made of water. It takes a lot of energy to change the temperature of that. So that's a good thing because you're made of water. So you can't change your temperature quickly. That was a joke. Now, let's look at the metals. Let's say you could have a custom-made cooking pot. And they ask you, okay, this custom-made cooking pot, which metal do you want us to make it from? How do you want us to make this custom-made cooking pot? Which metal would you use? Copper, aluminum, gold, silver? What do you think? Which one would be better? The one with the lowest specific heat or the one with the highest? Don't pick the one in the middle, highest or lowest. Which one is going to be the best one? Now, what are you thinking? Yeah, if you can have a cooking pot made of gold, that would be great. Because the specific heat of gold is low. So what that means is it does not take a lot of energy, it would transfer the energy to your food. So if you have a low specific heat, it doesn't take too much energy to raise the temperature of that. So if you can't afford gold, silver is pretty good too, right? Usually copper pans and pots are better than aluminum. You can see it has to do with a specific heat. It's kind of cool that you know that. Alright, so hopefully you understand the concept behind the specific heat. Now what we're going to do, let's do a practice problem. Let's do a practice problem to use the equations that we just talked about. Okay, let's do a practice problem. Here is our practice problem. How much energy in calories? What am I doing to you guys? How much energy in calories is released or absorbed when 30.0 grams of water liquid at 96.0 degrees Celsius cools to 20.0 degrees Celsius. Water liquid specific heat is 4.184 joules over gram degrees Celsius. We usually give the specific heat numbers to you. Okay, now when you read this, the first thing you should say, okay, this is talking about a temperature change, right? Because the temperature is changing. So if it's talking about temperature change, I'm going to put down the equation for temperature change, which is mass times specific heat times T final minus T initial. Then I go, okay, I'm just going to plug it in. Is mass given to me? Yep. How much do I have? I have 30.0 grams of water. Specific heat of water liquid because it's liquid. How do I know it's liquid? Because it's at 96 degrees, so it's liquid. Is 4.184, and my T final is 20, and my T initial is 96. And the units are all okay. I have degrees Celsius, I have grams, and that's what I want. So if I plug everything in, what I end up getting is negative 8912. What's the unit? Joules. What does this mean? What does this mean? What does a minus means? This is an exothermic reaction. The energy was released. So when you have minus or plus for energy, all it means is was energy released or was energy absorbed. So I plug it in, what I end up getting is joules, but that's not what the question asks you for. What does the question ask you for? Calories. Then I can convert joules to calorie. I know how to do that. 1 calorie is 4.184 joules. Coincident? No. So the joules will cancel out, and what I end up getting, 3 sig figs, I better pay attention to my sig fig, negative 1230 calorie, lowercase c. Okay, that wasn't bad. Again, exothermic reaction because I have a minus energy over there. Temperature change, not bad. It's not bad at all. You know the equation, you know the unit, and then look at the specific heat to figure out the unit, and all you have to do is just plug it in. So, T change, you got it down. What's the next thing we have to talk about? The next thing we have to talk about is P change. The next thing we have to talk about is P change. If you remember, what we said was that the equation for P change was what? The equation for P change was energy equal mass times delta H of phase change. Now let's go over this delta H of phase change. I was so vague about it. What am I talking about when I talk about phase change? I said it's a constant, right? If you remember, I said this is a constant. I'm going to give you this constant for water. For different liquid, you're going to have different constants, which will be given to you. So, phase change, we talked about it. Go at the beginning of the lecture, right? We said that fusion is what? Is melting. So I have delta H of fusion, when solid goes to liquid. That number is 333 joules per gram. What's the opposite of fusion? It was freezing, right? Go back to the lecture at the beginning. I'm not going to give you that number actually. Then is delta H of vaporization. Go to that chart at the beginning so you know what's going on. And that one was 202,260 joules per gram. And then I have delta H, opposite of vaporization was condensation, right? Vaporization, liquid to gas. Condensation is gas to liquid. I'm not going to give it to you. Okay. Now, I'm going to put up the chart that I said when you go to Chem 1B. Then you're going to think about me like, she wasn't that bad. She gave us this chart. Solid, liquid, gas. You come down, endothermic reaction, you agree? You go up, exothermic reaction. Also, we can go from solid to liquid, liquid to gas, gas to liquid, and then liquid to solid. Now, I said for fusion, when you go from solid to liquid, what is this number? 333. And for here, for vaporization, this number is 2260. I did not give you for freezing and condensation. Why didn't I give it to you, these numbers? So, I need this much energy to come down here. How much energy do I need to go up? So, think about it this way. I need this much energy to go up. When I'm coming down, it's the same distance. Now so I went up, I used energy, and it's positive because I needed energy to go up. When I'm coming down, it's the same distance. So it's the same amount of energy, except when I'm coming down, now I'm releasing that energy. So you go up, you come down, same distance, same amount of energy, just up is endo and you coming down is exhale. So what would be this number for freezing? Negative 333. Condensation, negative 2,260. You guys got it? So same distance, think about it that way. Same amount of energy coming down, going up, it's just coming down plus going up negative. So usually on the exam, I give you fusion and vaporization, and you have to know that the other ones, you just read the opposite. So far so good? Okay, so now let's do a practice problem, okay, with phase change. Let's do a practice problem with phase change. Okay, here's my problem. How much heat is released or required to convert so how much heat, which is energy, is required or released to convert 25.0 grams of H2O liquid at 100 degrees to H2O gas. Now, I know I'm doing a phase change. I go, okay, it's a phase change, so I'm going to write down energy is equal mass times delta H, okay? Now, what type of phase change am I doing here? What type of phase change am I doing here? So solid, liquid, gas, put this up every time. You go down here, endothermic, you go up here, exothermic. What am I doing over here? I'm going from liquid to gas. I'm going from liquid to gas, right? Okay, so that's the heat of vaporization. Nice job. Now, can I do a phase change? I can. And the reason that I can do a phase change, you can only do a phase change for water at 0 or 100 degrees. And I am at 100 degrees. So yes, I can do a phase change. Okay? All right, what is my mass? My mass is 25.0 gram. Delta H of vaporization, I just give you all those numbers a minute ago. If you look at that number, it's 2,260 joules per gram. So the grams can cancel out. What I end up getting is positive 56500 joules. Now, what type of reaction is this? It requires energy, it's an endothermic reaction, and I already knew that because when I'm going liquid to gas, that's an endothermic reaction. So it requires energy. And it makes sense because in order to melt ice, or in order to make the liquid to go to gas, you have to heat it up, don't you? To make the liquid go to gas, you have to heat it up. So you have to apply energy. So it makes sense that this is an endothermic reaction because you have to apply energy to make this reaction go, to make the liquid go to gas. So it makes sense that we have an endothermic reaction and have a positive sign. So far, so good? Okay. Now, last thing I'm going to do, I want to give you a take-home problem or an at-home problem since you're home. This should keep you busy and off the streets. Here is the practice problem. It has to do with phase change, of course, and the T change. How much energy is required or released? How much energy is required or released to convert 18 grams of H2O solid at minus 10.0 degrees Celsius to H2O liquid at 110 degrees Celsius. And all the constant, you already have all those constants in your notes. So you can use all those constants that you have. Now here's the thing. Here's my hint to you. And I need you guys to do this before you watch the next video. I haven't made it either, so you have time to do it. So what I'm converting solid to liquid, right? But in order to do any phase change, for water, you have to be at 0 or 100 degrees. And we're not at that. So there's some T change and there's some P change going on. Look at the graph that I have given you guys and then try to do this. Okay, so do this one, and next time, the first thing we're going to do this, and then we're going to move on to the next part. Okay, good job. Hang in there.